In this module, we will study techniques for designing the motion of the follower from partial specification of the motion. In particular, two types of partial specifications that we will be considering is the critical extreme position and critical path motion. In the critical extreme position, the endpoints of the motion are critical. For example, let's look at the picture here. The picture shows the schematic of an oscillating follower. L and R are the two extreme positions of the follower. In critical extreme position, the partial specification involves specifying or stating when the follower will be at position L and for what duration. Similarly, when the follower would be at position R and for what duration. On the other hand, in critical path motion, apart from the specification of the endpoints, we are also interested in the displacements or velocities along the motion. For example, we may say that from the beginning to the midpoint, the follower should have a constant velocity or a constant acceleration. In this module, we will be focusing on critical extreme position. Now, there are multiple types of critical extreme position problems. For example, we can have a no-dwell or rise-fall motion in which the follower has to move between the extreme positions, but it does not stay at those extreme positions. Staying at those extreme positions is called dwell, and moving to these extreme positions is called rise or fall. The terminology rise and fall comes from the assumption that the follower is oscillating vertically. However, even if the follower is oscillating horizontally or the follower has an angular motion, the discussion that we will do here holds. The use of rise and fall is just for convenience. We can also have a single dwell motion where we rise and then fall and then we dwell or then we stay static for a certain period of time. We can also have double dwell motion of the follower, which is what you saw in the valve operations that we had seen before. And in the double dwell, you dwell at one position, then you rise, then you dwell again, and then you fall. Of course, we can generalize this to multi-rise, multi-dwell, multi-fall motion. Now, depending on the type of critical extreme position given to you, the motion program or the functional relationship between the follower motion and the input shaft angle will change. And what we will learn now is to how to design this functional relationship. We will use the double dwell as an example. However, the procedure is very general and it applies to all these types of motions. Let us first look at an example of a partial specification of a cam timing diagram. The x-axis on this figure can either be the cam angle or the time. The cam angle is between 0 and 360 degrees, which basically implies that we are interested in one revolution of the camshaft, and the time here is given between 0 and 1 seconds. Now this may not be 1 second, this may be 2 seconds, half a second, and the value of the time actually depends upon the angular speed. For example, here the angular speed is 2 pi radian per second. The y-axis is the displacement or motion of the follower. If the displacement is linear, the units will be millimeters or inches, and here I am showing the displacement as 1 millimeter or 1 inch. Now the x-axis or the motion of the camshaft is divided into 4 phases corresponding to the low dwell, the rise, the high dwell, and the fall. During the low dwell, the displacement is 0 as shown here. And in this example, the low dwell occurs over 90 degree of camshaft rotation. During rise, which occurs between 90 degree and 180 degree of camshaft rotation, the follower goes from the low dwell to the high dwell. How this curve looks, that is not yet specified here. That is what we have to design. It is also specified that the follower stays at this high dwell position for 90 degrees of the camshaft rotation. And then during the last 90 degrees or between 270 degrees and 360 degrees, the follower will come back to its original position or will fall back to its original position. These 90 degree, 180 degree, 270 degree, these are just examples. In general, it can be any angle. So in general, my cam timing diagram will look something like this, where I have cam angle as the x-axis and the motion as the y-axis. Note that I can use cam angle as the x-axis because I am assuming that the angular velocity of the camshaft is constant. Also, I can set the 0 degree rotation of my cam angle anywhere I please. And just to show that, here you will see that I am saying that the rise motion starts at 0 degree of the cam angle. Then we have a high dwell between theta 1 and theta 2, and then a fall motion between theta 2 and theta 3, and then there is a dwell motion between theta 3 and 2 pi. It is important to note that since the motion is oscillatory, we are interested in one revolution of the drive shaft or camshaft. From this partial specification, what we have to do is design these curves. More precisely, we have to form what is known as the SVAJ diagram, and this is the first step of cam design. In the SVAJ diagram, S stands for displacement, V stands for velocity, A for acceleration, and J for jerk. And these are all functions of t or theta. V equal to ds dt. A is time derivative of velocity, which is dv dt, and the jerk is the time derivative of acceleration, which is dA dt. Now what we will do is that instead of taking the derivatives with respect to the time, we will take the derivatives with respect to theta. And this is only valid when the angular speed omega of the camshaft is constant. So we will use V equal to ds d theta, A equal to dv d theta, and J equal to dA d theta. So the small SVAJ will denote that the quantities are a function of theta. The capital SVAJ will denote that the quantities are a function of time. And as I stated before, the process of cam design begins with forming these SVAJ diagrams from the cam timing diagram or partial specification of follower motion. This is an example of what an SVAJ diagram would look like. This portion here is the rise, this portion is the high dwell, this portion is the fall, and this portion here is the low dwell. At this point, what I want you to take away from these diagrams is that these curves are continuous functions of time or theta. And our goal is to design these curves so that these continuity properties hold. Now let us look at some intuitive ways to design these curves, which are incorrect in the sense that they will not satisfy the continuity requirements. So the first and simplest choice that you can make is to use a linear displacement curve for the rise and the fall motion. If we do that, it would imply constant velocity for the rise and constant velocity for the fall. But when transitioning from the low dwell to the rise, I have to change from zero velocity to constant velocity instantaneously, which is shown here by this step function. So the acceleration at this point would be infinity. Or in other words, the acceleration curve is not continuous anymore. Similarly, the jerk curve will also not be continuous. So although having constant velocity motion is a simple and intuitive way of designing the motion in the rise and the fall phase, it is not acceptable. Now I could go to a constant acceleration motion or a parabolic displacement motion. For part of the rise motion, I have a constant acceleration and then I switch to a constant deceleration. However, this is not a good motion because at these points my jerk becomes infinity. Another option is to use simple harmonic motion. And for the simple harmonic motion, we will restrict ourselves to look just at the rise curve. The fall curve will be analogous. Let us first define some notations. Let beta be the angle over which the event, that is rise or fall, occurs. H is the distance by which the follower should rise or fall. Then for simple harmonic motion, the displacement curve should be defined as h by 2 1 minus cos pi theta by beta. Now the first question is, why should it be defined like this? Although I am not going to get into the details of the mathematical derivation here, it comes from the boundary conditions of the rise motion. When the rise motion starts, I am at the low dwell, so S is equal to 0. When the rise motion ends, we should be at the high dwell, so S equal to H. Furthermore, since the follower starts from the low dwell, where it is stationary, the velocity should be 0 at the beginning of the rise motion, and the velocity should also be 0 at the end of the rise motion. Now, if you consider this boundary condition, then for a simple harmonic motion, one can prove that this is the kind of displacement curve that you have to use. And you can verify it by putting in these boundary conditions. For example, when theta is equal to 0, this term here becomes 0. So cos of 0 becomes 1 and S becomes 0. Similarly, when theta is equal to beta, this term here becomes pi, and cos of pi is minus 1. So we have S equal to h by 2 into 1 plus 1, which is h. From the displacement curve, we can get the velocity curve by doing ds d theta. From the velocity, we can get the acceleration by doing dv d theta. And from the acceleration, we can get the jerk by doing dA d theta. I'm not taking the derivatives here because these are simple derivatives that I believe you can take. The point to note here is that although the displacement and velocity curves are continuous, the acceleration curves become discontinuous because at this point, the acceleration was 0. We were in the low dwell, which manifests itself in the fact that the jerk becomes infinite at the extreme points of the rise motion. So this simple harmonic displacement curve is also not acceptable. This intuitive discussion leads us to the fundamental law of cam design, which states that the cam follower function must have continuous velocity and acceleration across the entire interval, thus making the jerk finite. For a rise or fall curve, this means that there should be 0 velocity and 0 acceleration at both ends of the curve. Why? Because we are moving from a low dwell to a high dwell, or a high dwell to a low dwell, or we are moving from a stationary position to another stationary position. This is the most important fact that you have to remember for designing follower motions of cams. And this is what we will be using throughout the rest of this module and the next module. Apart from the fact that the cam follower motion should obey the fundamental law, there are 3 other desirable characteristics of the follower motion. First is that lower peak accelerations are preferred. Second, lower peak velocities are preferred. And third, smoother jerks are preferred. Lower peak accelerations implies that the force that will be required to move the follower that will be lower. Lower peak velocity implies that the energy that has to be put in to move the follower that has to be lower. And smoother jerk actually implies lesser vibrations. Up to now, I showed you some unacceptable cam functions, which included the constant velocity or linear displacement, constant acceleration or parabolic displacement, and the simple harmonic motion. Now, using the fundamental law of cam design, you can also show that the cubic displacement is also not desirable. I leave it to you as an exercise to show this, and at the end of the module, you should have all the tools that you need to show that the cubic displacement curve is not an acceptable cam function. There are 2 key classes of acceptable cam functions for double dwell follower motion. The first 4 here form a class, and the last 2 here forms another class. The acceptable cam functions for double dwell or RDFD follower motion includes cycloidal displacement or simple harmonic acceleration, modified trapezoidal acceleration, and modified sine acceleration. And these 3 functions can be included into what is known as the SCCA class of curves, or sine constant cosine acceleration class of curves. This is a piecewise continuous curve, and it can be mathematically shown that all these functions are acceptable cam functions, that they will obey the fundamental law of cam design. Now, the details of this is given in the book. However, for the purposes of this class, we will not go into the details of these functions here. One reason is that these functions are mainly useful for double dwell follower motion. A more general class of methods that's not only useful for double dwell follower motion or in general for critical extreme position motion, but also for critical path motion, are the polynomial displacement curves, or its generalization, which are the piecewise polynomial displacement curves or splines. And we will focus on designing polynomial displacement curves. Let us now look into the mathematical details of the process of designing polynomial displacement curves. Our objective is to design a polynomial displacement curve for the rise motion such that the fundamental law of CAM design is satisfied, which means that the position, velocity, and acceleration curves are continuous. We are restricting ourselves to the rise motion because the design of the displacement curve for the fall motion is analogous. First, let us introduce some notation. Let beta be the angle over which the rise event occurs, that is beta is equal to theta 2 minus theta 1. Theta 1 is the angle at which the rise event starts, theta 2 is the angle at which the rise event ends. H is the distance by which the follower should rise, so H is this value. We define a variable theta, which is a running variable over the rise event, such that theta is equal to 0 at the start of the rise event and theta is equal to beta at the end of the rise event. Let S be the displacement of the follower, S equal to 0 at the start of the rise event and S is equal to H at the end of the rise event. A polynomial displacement curve of the follower has the following form: S equal to C0 plus C1 theta over beta plus C2 theta over beta whole square plus dot dot dot. What I want you to note is that the polynomial is in theta over beta. Our first step in designing the displacement curve is to choose the value of n, or the degree of the polynomial, based on the boundary conditions that we can obtain from the fundamental law of CAM design. Now we have seen before that at theta equal to 0, the displacement S should be 0, and at theta equal to beta, the displacement S should be H. From the fundamental law of CAM design, since the velocity should be continuous and we are going from a low dwell, at theta equal to 0, the velocity should also be 0. And since we are going to a high dwell, therefore at theta equal to beta, the velocity should be 0. Similarly, because we are going from a low dwell to a high dwell, where the follower is stationary, the accelerations at the two endpoints also has to be 0. So in total, we have 6 boundary conditions. If we choose a polynomial of degree 5, it will have 6 unknowns: C0, C1, C2, C3, C4, and C5. And these 6 unknowns can be obtained so that the 6 boundary conditions are satisfied. So the degree of the polynomial that I should choose is 1 less than the number of boundary conditions available to me. This is a general rule that is always true. Now, given the choice of the displacement curve, the velocity is given by ds d theta, and if we take the derivative of this expression here with respect to theta, then we will get the expression in here. Although this derivative is fairly straightforward, but since this step is very important, I will show you how to take this derivative, and I will show it to you in a general form. So the terms here are of the form ci theta by beta to the power of I, where I ranges from 1 to 5. Now if I do d theta of ci theta by beta to the power of I get I times ci by beta to the power of I theta to the power of I minus 1. This is because ci and beta to the power of I are constants, so they come out, and d theta of theta to the power of I is I theta to the power of I minus 1. I can rewrite this as I ci by beta theta by beta to the power of I minus 1. And that is what I have done here. So substitute I equal to 1. You get the first term here. For I equal to 2, you get this term. For I equal to 3, this term. I equal to 4, you get this term. And I equal to 5, you get this term. In the same way, I get the acceleration by taking the derivative of v with respect to theta. The derivative of this term will be 0 because it is constant. The derivative of this term gives me this, and this beta comes out to the beta squared term here. The derivative of this term gives me this, and remember that one of the beta comes out to this beta squared term. The derivative of this term here gives me this, and the derivative of this term here gives me this. Now that I have the expressions for V and A, I will use the boundary conditions to get the unknowns C0 to C5. These are the three expressions for displacement, velocity and acceleration that we obtained in the previous slide. At theta equal to 0, S equal to 0. So substitute theta equal to 0 in this first equation here. Each one of these terms are 0. And the left hand side here is 0 at theta equal to 0. So C0 has to be 0. Now we also know that V is equal to 0 at theta equal to 0. So at theta equal to 0, again this term is 0, this term is 0, this term is 0, this term is 0. V is equal to 0, so C1 has to be equal to 0. Similarly, A equal to 0 would imply that C2 equal to 0. Again, this term is 0, this term is 0, this term is 0. So 2C2 by beta square is 0, and therefore C2 has to be 0. So from the first three boundary conditions, we get that C0, C1 and C2 are 0. In essence, that means that the first three terms in the displacement curve is not there. Similarly, these two terms in the velocity curve is not there, and this term in the acceleration curve is not there. At theta equal to beta, S equal to H. So when theta equal to beta, this is 1, this is 1, and this is 1. So on the right hand side, I have C3 plus C4 plus C5. And on the left hand side, I have S equal to H. So I get this equation. Now at theta equal to beta, which is at the end of the rise motion, I have V equal to 0. So theta equal to beta implies this term is 1, this term is 1, this term is 1, and V is 0. So what I have is 1 by beta 3C3 plus 4C4 plus 5C5 equal to 0, which implies 3C3 plus 4C4 plus 5C5 equal to 0. Similarly, at theta equal to beta, this term is 1, this term is 1, this term is 1, and A equal to 0. So I have 6C3 plus 12C4 plus 20C5 is equal to 0. So I have three equations here with three unknowns, and I can solve for these three unknowns C3, C4, C5 from these three equations. And if I solve them, I'll get C3 is 10 times H, C4 is minus 15 times H, and C5 is 6 times H. And remember, I do not need the numerical value of H to compute this C3, C4, C5. The coefficient matrix of C3, C4, C5, that's a constant matrix. So I can invert it and I can obtain C3, C4, C5 in terms of the H. Now substituting the values of C0 to C5 that we obtained in the previous slide, we obtain this displacement curve. In this displacement curve, only terms of degree 3, 4 and 5 are present. Therefore, this is also called a 3, 4, 5 polynomial. Similarly, the velocity and acceleration curve we can obtain by substituting C0 to C5 in the expressions for the velocity and acceleration that we had before. The jerk can be obtained from dA d theta. Now, if you look at the plots, this is our displacement curve, which is the plot of this equation here. This is the velocity curve, this is the acceleration curve, and this is the jerk curve. Now the displacement, velocity and acceleration are continuous and the jerk is finite. However, here you will see that the jerk has a jump. Fundamental law of CAM design does not preclude this. Fundamental law of CAM design only requires that the jerk be finite. It doesn't require the jerk to be continuous. However, if we want the jerk to be continuous, then we need to make sure that the jerk is also 0 at the beginning and the end of the rise motion. If we put in the boundary conditions that the jerk is also 0 at the beginning and the end, along with the boundary conditions for the displacement, velocity and acceleration that we had before, we have 8 boundary conditions. This implies that we need to use a 7-degree polynomial to satisfy the 8 boundary conditions. So our displacement curve will now look like this. Following the similar procedure as before to compute C0 to C7, we will get the 4, 5, 6, 7 polynomial, which is shown here. One problem in your assignment will be to derive this equation. The displacement, velocity, acceleration and jerk curve will look like this. And you can see that all the curves are continuous, they are 0 at the end, and everything is finite. This may indicate that the 4, 5, 6 polynomial is always preferable to the 3, 4, 5 polynomial. However, there are some disadvantages of the 4, 5, 6 polynomial. If you look at this picture here, where there is a comparison of 5 double-dwell functions, you will see in the velocity curve, 4, 5, 6, 7 polynomial leads to higher velocities. Higher velocities would imply higher kinetic energy requirement. Similarly, the acceleration of the 4, 5, 6, 7 curve is higher, which would mean that you need higher force. Although these curves here have modified trapezoid, cycloidal, and modified sine also, for the purposes of this class, I want you to focus on just the 3, 4, 5 and 4, 5, 6, 7 polynomial, so that we understand that there is a trade-off in making the jerk smooth and the energy and the force required to do it.